Uh, Hi guys, this is Raghuram Raju Narimpalli, and now I'm taking you over through the analysis of algorithm project. And for this project, the topic I have selected is closest pair of points. So, what is exactly the closest pair of points? This problem involves finding the pair of points in a set of n points in a two-dimensional space with the smallest distance between them. So it is an important problem, in computer science and mathematics, as it has many practical applications in various fields such as mapping, robotics, image processing, and more. So the problem is important because it helps in determining the optimal solution for finding the closest pair of points, which is useful in various applications where efficiency is critical. So for this, to tackle this problem, I have taken like two algorithms. One is brute force algorithm, and the second one is divide and conquer. So I will take you to these both algorithms, and we will find the solution how to find this closest pair of points, and we will you know find the differences between both the algorithms, and we'll get in conclusion like which one is the most optimized one and their running times. So yeah, that's the problem definition for this. And the first algorithm that I've chosen is brute force algorithm. So the brute force method is a straightforward algorithm used to solve the closest pair problem. It involves comparing the distance between every pair of points in a set and returning the pair with the smallest distance. Here is how it works. Given a set of endpoints, choose any points to find the if you wanted to take the larger input, you can give it like 10 power 3 or 10 power 4. If you wanted to find the test cases for the smallest points, you can just take 2 points. So we'll compute the distance between 2 points. So after that, we move on to the next pair of the points and repeat the same step to like compute the distance between 2 points. So repeat this process for all possible pairs of points in the set, and return the pair with the smallest distance. So that's what this algorithm explains. We'll just take the points like if you wanted to take 2 points, so it will give like x and y coordinates of 2 points, and after that we will just set the closest pair to run and minimum distance to infinity. After we will get the two loops, two iterative loops, and to first we will take 1 point and we will check the distance of 1 point to all the other points, and we will get the distance. If which of the distance is smaller, then it will just return the closest pair. So that this is like simply straightforward algorithm, but there are few issues with this algorithm. It takes O of n square time complexity. So the brute force method is O of n square, which means that the algorithm takes proportional to the square of the number of points in the set. For large set of points, this method cannot be can be very slow and impractical. However, it is useful for a small set of points, or as a baseline algorithm for comparison with other methods. So until 3 points, the complexity will be just O of 1, and once the points are increased, then the O of n square keeps on increasing. So it takes a lot of time to totally complete this for loops, because we use two for loops inside each. So the second algorithm that we have taken is divide and conquer. The divide and conquer method is more efficient algorithm for solving the closest pair problem compared to brute force method. It involves the following steps. First is to sort the points with both coordinates x and y respectively. After that, we'll divide the sorted set into two halves. Uh, Two halves with a vertical line passing through the median. So for px, we're dividing it to like qx and rx, and for the py, we're dividing it to qn and ry. After that, recursively find the smallest distance in both halves. So take the minimum of two smallest distance found in the previous step, and we call it delta. So after finding the smallest distance of the both the halves, So we will like consider which is minimum of those 2 points, and we'll call it as delta. After that, what we do is we'll find all points in the set that are within delta of the median lines, and we'll sort these points according to their y coordinate. So after sorting all these with y coordinates, we will compare each point to its 15 neighbor points in sorted array and compute their distance. Why? Because we are taking 15, because it will be like less than delta by 2 distance, sorry, less than delta distance, because we have to get the distance which is less than delta in order to compute the closest pair. So if it is more than 15 points, it will be like more than delta, so we don't need to worry about more than 15 points. So like less than 15 points is enough to compute the delta here. So if a smaller distance than delta is found, then we will update the delta to that distance, and we'll simply return that points and distance. And if we didn't find, then we'll simply return the delta that we got from both the halves. It's the same explanation. And the time complexity of the divide and conquer method is O of n log n, which is much faster than the brute force method for large sets of points. However, the algorithm can be slower for small set of points due to the overhead of the recursive calls. Nevertheless, it is an efficient algorithm for solving the closest pair problem and is widely used in practice. So this is the source code that I have developed from this pseudocode that I have built. And the RT analysis is like, it's simple because we are dividing it into the two halves. It will be two subsets of size of n by 2. So a is equals to 2 and b is equals to 2. So using the master's case 2, so master theorem case 2, it is applicable that t of n equals to 2 t of n by 2 and c of n. So the complexity is proved that O of n log 2 n. Why I'm using n log 2 n? Because we are dividing it into the two halves. So I've given 2, but it doesn't matter whether it is 2 or 10. Anything would be fine to compute the running time analysis. And same with the brute force, because we are using two for loops, and each for loop iterates for each point to compute the distance. So the complexity will be O of n square, because n is the input. And after, what I'm doing is the input for the closest pair problem is a set of n points in a two-dimensional space, where each point is of course represented its x and y coordinates. The set of points can be represented in a variety of ways, including as a list or an array, which with each point represented as a tuple or a structure containing the x and y coordinates. For example, if we have a set of 4 points with the following coordinates, like 1 2 3 4 5 6 7 8, so the array will be like those all 4 points will be included in an array. So first point will be like 1 2, and second point will be 3 4, and so on. So if these 4 points are the input, then output will be simply the closest, which is the closest pair. We'll get that as an output, which is 1 comma 2 and 3 comma 4, and also the distance that is calculated with the formula equilibrium distance, and the distance is like 2.83 between 0.12 and 3 4. So output will be like this, like 1 2 3 4 and 2.8. Let me show you the output. So like this, these two are the closest pairs, and this is the distance between these two closest pairs. And I'm also computing the running time. So this is all I will explain when I'm executing the program, and I will show you the output when I run this code, and I will explain in detail after some time. So that will be the input and output. And when it comes to applications, the closest pair, let me just take you to the applications. Yeah, so the closest pair problem, it is a fundamental computational geometry problem that involves finding the pair of closest points in a set of points This problem has numerous applications in various fields, including mapping, robotics, and image processing. So when it comes to mapping, the closest pair problem has important applications in mapping, particularly in geographic information system (GIS) and spatial data analysis. For example, in GIS, the closest pair problem can be used to find the nearest facilities, such as hospitals, schools, or fire stations to a given location. This can help in decision making for urban planning, emergency management, and logistics optimization. And when it comes to robotics, in a robotic arm, the closest pair problem can be used to determine the distance between the end effector and the objects it needs to grasp or manipulate. Similarly, in autonomous navigation, the closest pair problem can be used to identify the closest obstacle or boundary that the robot needs to avoid. In image processing, it can be the problem can be used to align two images by finding the closest corresponding points between them. In feature matching, the closest pair problem can be used to match key points between two images based on their proximity. In object recognition, the closest pair problem can be used to identify the closest match between an object in an image and a known template. So these are the applications and advantages of the closest pair problem and finding this closest pair problem. And so now let's get to the source code that I have developed for this to compute the closest pair. So this is the first code, which is brute force, and this is how I have developed here with some few test cases, like from small inputs to the large inputs. So this is where we will find the distance of 2 points using the Euclidean distance for problem. So in math, we have simply have a library called square root, have a method called square root. From that we can simply use the 2 points and we can get the distance using this command. And when it comes to brute force method, this is how I developed this function method. The input will be points here. So if it is if n equals to 2, then two some random points will be generated and will be given as an input to this method. After that, we will simply get the length of those points, and we'll just define some basic like best pair, best distance into this. And after that, we'll simply use the two for loops, nested loops, and for each point of n, we'll find the distance to all the other points. And in the same way, the second point, if I equals the second point, then it will be we'll find the distance of to the each point of this second point. And so we'll find the distance and best pair. And after all the at the end of the loop, we will get the best pair and the best distance, and we will return simply that best pair and best distance. So I will execute live here. So let me just comment these remaining other test cases, and let's get to the first test case, which is very small input, like just 4 points. So the input is 0 0 1 1 4 4 and minus 2 2. So our goal is to find the closest pair from these 4 points. So by seeing those inputs, we will simply get to know that 0 0 1 1 is the smallest pair here. And let's execute and check whether we're getting the 0 0 1 1 as the output or not. So you see, the test case 1, the closest pair is 0 0 1 1, and the equivalent distance is 1.414 of these 2 points. So this is how this test case 1 works. Let's get to the test case 2, and let me just comment this. Alright, okay, the test case 2, here I am giving like 6 points as input, 10 10 1 1 20 20 random points. And from by seeing these points, we can tell that 10 10 12 12 is the closest pair and have the least distance. So let's just run this, and you can see 10 10 12 12 is the output, and the distance is 2.828. And same with the test case 3. So in the test case 3, what I'm doing is I'm giving like some negative coordinates, 1 comma minus 1 minus 2 comma 2. So even though we're giving the negative coordinates, we should get the closest pair of 2 points. So by seeing the input, we can say that like 0 0 1 comma minus 1 are the closest points by just common sense, and we'll just round it, and the output is 0 0 1 1 comma minus 1. And in the test case 4, here what I am doing is I'm generating 100 random points here. Why? Because we keep on increasing the input. So the main goal is to find that how efficient the algorithm is and how effective it is, and how optimized and how much less the running time is. So these are our goals from this project. So when n equals to 100, I mean, we are generating some random 100 points between minus 100 to 100 at the random points, and the loop will run like 100 times. So the points 4 will have 100 random points. So that's how this command works. And so let's run this code, and the closest pair of these random points, we don't know what are the input we are giving. We are just giving some random points. From those random points, the closest pair is 9126 and 9224, and this is the distance between those 2 points. So this is how the random input works. And at the final stage, here we are giving n. It is up to the coder. Like if he wants to give 10 power 3, he will simply give n as 10 power 3. If he wants to go some more extent, then he can give 10 power 4. So 10 power 4 is a very large number, so it's going to take a lot of time if we give the 10 power 4. But 10 power 3, it's just normal number. So the code will execute faster because this is brute force. It's going to take a long time for 10 power 4, and 10 power 3 is it's okay number. So if I give n equals to some 10 power 3, so what it's gonna do is this for loop gonna iterate for 10 power 3 times. So the 0.5 will have 10 power 3 random points. So that will be the input for brute force. Sorry. So that will be the input for this brute force, and the output should be the closest pair of those points. And let me just run this. So it's asking for me the enter number of points I want to generate. So that will be 10 power 3, and just clicking enter. So from the random points that were generated, 10 power 3 random points, I've got these 2 points as the closest pair with the distance 2023.094. And here I'm generating the running time of this algorithm, because we have to analyze the running times, and from that we have to check the practical running time and the theoretical running time are somewhat like closer or not. So for that we have to get the running time of this particular algorithm. So to get the running time, I'm using command called time.time. So here my time will get start, and after that I'm computing the method, and the end time is time.time minus the start time in 2000. So this will give me in milliseconds. If you don't multiply with 10 power 3, it will be in seconds. So that will be my output. So that's how brute force works. If you see here, for 10 power 3, the running time is 351.23 milliseconds, and if I give 10 power 4, it will be like around maybe 35,000 milliseconds, or 3051 some milliseconds. So which is more running time, we don't want this much running time for this simple code. So we wanted to optimize this algorithm, and that's where the divide and conquer algorithm comes into the picture. And in a minute I will explain how divide and conquer works. So that's it. I have explained brute force, and the complexity will be of n square. And for each input n, like 1000 for 10 power 3, I will be running this algorithm 10 times. So I will note down all my running times here. So from there I will simply do the average of all these running times for n equals to 10 power 3. In the same way, if I wanted to give 2000, and this is my running time. So in the same way, with 2 into 10 power 3, I will be running this code 10 times, and I've noted down all my running times here for the input 2 into 10 power 3. In the same way, I've raised the input each 10 power 3 every time, and until 10 into 10 power 3. And I want all these averages in order to find the difference between the theoretical empirical RT and predicted RT. So this is the table where I have analyzed the empirical RT and the predicted RT. My input is from 10 power 3 to 10 into 10 power 3, and of course the as I already explained, for the brute force theoretical complexity is of n square. So n square will be the 10 power 3 square is 10 power 6. So this is how we got the theoretical complexity. And empirical RT is nothing but the average of 10 times of the input 10 power 3 running time, so that which is the average of all these running times, which is 351.95. In the same way, we have to find the average running times of the 10 RTs we did for each input. And the ratio is nothing but empirical RT divided by theoretical complexity. That means 351.951 divided by 10 power 6, which is 351.9 into 10 power minus 6. This is how ratio comes, and from this ratio we have to get the maximum ratio in order to compute the predicted RT. So here C1 equals to max of all the ratios, and from these ratios I found that R8, which is 367.1 into 10 power minus 6, is the maximum of all these ratios. And using that C1, so C1 will be 367.1 into 10 power minus 6, and using this we will be computing predicted RT. So predicted RT equals to C1 into theoretical complexity. So 367.1 into 10 power minus 6 into empirical RT is my predicted RT. So this into this is 367. Oh, sorry, not empirical RT. So sorry, the theoretical complexity n square. This is my mistake, sorry. 367.1 into 10 power minus 6 into 10 power 6 is 367.1. In the same way, we'll just multiply the maximum ratio with the n square. This is how I got the predicted RT. And using these two, empirical RT and predicted RT, I've plotted a graph, so which I've shown in the bottom. So this is my graph between algorithm 1 empirical RT and algorithm 1 predicted RT. So here you can see the graph is like almost very much closer for each input n, and my orange line is predicted RT, and blue line is empirical RT. That says my practical running times are slower, so getting like not slower, they're very much faster than, not very much, like similar, a little bit faster than the predicted RT that I've got. So this is how I plotted the graph for the empirical RT and predicted RT over the input n equals to 1000, like 10 power 3 to 10 into 10 power 3. So from this we can say, or it is clear that the theoretical complexity and predicted and actual RT values are broadly proportionate, indicating that the algorithm performs as predicted as a performance scale. So the ratio column, however, exhibits some variances, indicating that the actual running time may vary slightly from the theoretical complexity. So that's how I've done for the brute and force. And now the important algorithm, the optimized algorithm, divide and conquer, comes into the picture. um, because I've already shown you that for the larger inputs like 10 power 4, 10 power 5 and 10 power 6, the brute force, it's gonna take a long time to get the output because of its theoretical complexity or the nested for loops, and that's where the divide and conquer comes into the picture. So for divide and conquer, so all right, this is the second algorithm source code, which is divide and conquer method. So here I will just explain the algorithm, and later I will just go to the test cases. And the algorithm, as you already know, first I have uh, sorted all the points. Input is the points and number of points, and the points are sorted in x coordinates and y coordinate. Here I've coordinated with x coordinate. And when it comes to the recursive method, here what I'm going to do is, if n is less than or equals to 3, which is of course comes under brute force. We are using brute force for n less than or equals to 3 because the complexity will be O of n. And also brute force is straightforward, and also know that brute force works very well for the small set of points. So that's why if n less than or equals to 3, brute force is best algorithm, and simply we can go straight forward and the complexity will be O of 1. And if not, then what we do is we're gonna divide algorithm into two halves using the x coordinate and the y coordinate. When we use the when we sort the points with x coordinate, we divide the points into two halves, and from left to mid it will be they all comes under qx, and from mid to right points it will be like rx. Same with the sorted with y coordinate points, also qy from left to mid, and ry from mid to right. So from here what we're gonna do is we're gonna check each point from each half which is the closest pair. So using recursive method, like recursively find closest pair in each half, and q0 and q1 will have the closest pair in the qx and qy half, and r1 will have the closest pair of rx comma ry half. I think you got the point. So from here what we're gonna do is we're gonna get the delta, which is the minimum distance of these two. Here I got the points and distance of those 2 points, same here, and the delta will have the smallest distance of these two halves. And after that what we're gonna do is we're gonna check the points within from the median and within the radius of delta, and those points we're gonna order them in the y coordinate. And this step do that we're gonna coordinate we're gonna order them in the sort them in the y coordinate, and the points we're gonna check within delta from the midline. So what I'm doing now is, from these 2 points whichever is the closest, we're gonna get that as the best pair and the best distance. And from in those sy points we're gonna check whichever is have the less than best distance, they're gonna get the best pair and the best distance. And we only check less than 15 points because more than 15 points, of course the it gonna cross the delta. So in that case we're gonna get whichever is the best here. If we got any distance less than 15 points, that we might get the points which are less than delta. So in that case we have to make sure the best pair will be those 2 points, and the best distance is the distance between those 2 points, and we're gonna return the best pair and best distance. These are the equilibrium distance on the brute force method that we have in this closest pair. And we're gonna return the closest pair rectangle of both coordinates px and py, like sorted with x coordinates and sorted with y coordinates. And so what we're gonna do is, from first test case the points we are given is 0 0 1 1 4 4 minus 2 comma 2. So I mean, looking at the points, we're gonna get that 0 0 1 1 are the closest pairs. And let's run this program and see whether we got 0 0 1 1. Yes, we got this 0 0 1 1, and with the distance 1.414. So for the test case 2, which is like 6 points, and these are the points same we used in the brute force, and from there we can say like 10 10 12 12 are the closest points. Looking at those points, and let's run this 10 10 and 12 12. 2.82 comma 84 is the distance between those 2 points. And when it comes to test case 3, we're using the negative coordinates, and by seeing them 0 0 1 comma minus 1 have the closest points. And let's just run this, and yeah, 0 0 1 comma minus 1 has the closest points. And in the test case 4, as we know, we are using 100 points. Using this for loop, we're going to generate 100 random points between minus 100 comma 100 as each point, and so points 4 will have the 100 points. Let's run this. So we got minus 40 minus 16 minus 40 minus 15 as the closest points with the distance 1. That's how test case 4 work. And the main test case is like for large numbers. So for this large numbers, I'm going to give some large input, which is 10 power 3 for our project. And this is the closest pair that I've got, and the closest pair distance is this, and my running time is this, because you know we are analyzing the running points and we're going to get the empirical and predicted RT. We need the running time of this particular algorithm. That's why I've started my time here and ran the algorithm here, and my end time will be here. Because I get the time in seconds, I want it in milliseconds, so that's why I multiplied it with 1000. So here I will get the running time. End time is my running time in milliseconds. So if you compare the test case 5 with n equals to 1000, here I got the running time with 33 milliseconds. But when in brute force, let's say if I run this only test case 5, you see the running time is 405. Here I got 33 and here is 405. You can simply see how optimized the divide and conquer algorithm gives, and how fast it is running. It's just 33 milliseconds, and for brute and force it's 405 milliseconds. That means even for 10 power 4 10 power 5 brute force algorithm gonna give you the output very quickly, but the brute force might take more than 10 minutes 20 minutes to give you the output for larger inputs 10 power 4 and 10 power 5. So I think that's it. I have explained pretty much from this algorithm. We're gonna return the best pair and best distance from this algorithm. From there we'll get the closest pair and closest pair distance for the n number of points that we're using. So again, the same way as I explained you, as I explained you in the for the brute force, I'm gonna run 10 times for each input 10 power 3, and I'm gonna raise the input n times each until I get the 10 into 10 power 3 as an input. So let me show you the table again. So this is my running time table. So these are my 10 running times for input 10 power 3, and from there I will get the average, which is my empirical RT. So same, I will raise the input 10 power 3 times more until 10 into 10 power 3, and for every input I will just do 10 times run, and I will get the average RT. So my main table, where I'm gonna calculate the predicted RT. For predicted RT, my complexity, the input is n, which is 10 power 3 and raised by 10 power 3 each time, and my complexity for this algorithm is n into log 2n. Why I gave 2 is because As I already told you, I'm dividing this points into two halves, so that's why I'm gonna give 2. Or you can, that doesn't matter, any base is fine. 10 is fine, because at the end the predicted RT will not affect with this base. So because where we're gonna get the constant from ratio, which is maximum, so that's why any base is fine. So n log to n, when n equals to 10 power 3, this is how I got the value for n log to n. Same for all the 10 into 10 power 3. And the empirical RT is nothing but my average RT that I got for each input 10 times. This is my average, and ratio, which is empirical RT divided by theoretical complexity. These are the values I got, and from these the maximum RT I'm gonna take is 2.521, which is R2. Of course R1 is greater than R2, but I didn't take R1 because R1 comes under outlier, because if you see the remaining other running time ratios, when compared to remaining other ratios, R1 is like very large ratio. So that's why if we ignore the outlier, which is R1, then our predicted RT will be is more reliable, like more proportional to empirical RT. So that's why we're gonna remove the outlier. From there I got the C1 is 2.521, and my predicted RT is nothing but the maximum ratio that I got, which is C1 into theoretical complexity. So if I multiply my C1 with all these things, these are the predicted RT I got. So when I plot the graph for empirical RT and predicted RT for algorithm 2, this is how it looks. So of course my predicted RT is more, which is the orange line, and my empirical RT is less, which is my practical values. My practical running time is less when compared to predicted RT. That means my algorithm works very my algorithm works good. So my code is running fine. So that's how I can come to a conclusion that it works fine. So I think that's it pretty much. So I plotted 3 graphs. One is the empirical RT versus predicted RT from my algorithm 1, which is this I already explained, and same with the algorithm 2 and predicted 2. Same, I mean for my divide and conquer, this is how the algorithm looks. And the third one is the empirical RT between my algorithm 2 and algorithm 1. So from that we can know, I mean from the code or from the running time, we already know that the divide and conquer works much faster than the brute force. As I already shown you the running time values for n equals to 10 power 3 to 10 to 10 power 3. The running time is almost 10 times less than the algorithm 1 brute force. So when I plotted those values, this is how my graph looks like. This is, let's say this is my brute force running time for each input, and you can see when compared to the brute force, my divide and conquer empirical RT is almost is a straight line near to the 0, and but those are not 0, those are some values. But when compared to the brute force running times, my divide and conquer running time looks like this, almost 0, but they're not 0. There is some time, but when compared to brute force, they almost looks like 0. That means they're much faster than the brute force. The divide and conquer works very much effective than those. And I think that's it. I think pretty much I have covered everything. So I don't think so I missed anything. So I used Python program. Sorry, I think I forgot to mention this before. So I used Python programming here to compute the closest pair problem. And yeah, I think I explained pretty much about the algorithm and the code, how it works and how I have developed. And RT analysis, outputs, and graphs. I think running time, tables. I think, yeah, pretty much I have explained about everything. And yeah, so in summary, the closest pair problem involves finding the pair of points in a set of n points, a two-dimensional space, with the least distance between them. So the problem is important in various applications such as mappings, robotics, and image processing. So there are two main algorithms, for solving this: the brute force and divide and conquer. So the brute force method involves checking the distance between every point of every pair of points, resulting in a time complexity of O of n square. And the second one is divide and conquer, involves sorting the points, recursively finding the smallest distance in subproblems, and merging the results, resulting in a time complexity of O of n log n. So the input for the problem is a set of n points in a 2D space represented by their x and y coordinates, while the output is the pair of points with the smallest distance between them along with the distance value itself. So yeah, in conclusion, the problem is a fundamental problem in computational geometry with various practical applications. Efficient algorithms such as the divide and conquer method makes it possible to solve the problem for large set of points efficiently, opening up new possibilities in fields such as robotics, mappings, and image processing. So that's it. That's my conclusion and my summary for all this for this project. And so these are some references uh, that I've taken to compute this problem, and that's pretty much from my side. And signing off, Raghuram Raju Nadimpalli. Thank you so much. Bye bye.